First, I would like to thank Professor Song-Han for organization and giving me an opportunity to give a talk at this conference. And thank everyone for being here at this moment to listen to my talk. So today's my talk is about an Erdős-Ko-Rado Theorem for cross-T intersecting families. So this is not about function field. This is about related topics. So maybe you may not be familiar with this topic. So I try to make some easy talk. So with some result and meaning of result and basic ideas, something like that. This is a joint work between Peter Frankl and Noride Tokushige, who live in Japan, and Mark Seegers and me, who live in South Korea. Here, Mark Seegers is in Gyeongbuk National University. Okay, so let me explain the organization. First, I will explain the Erdős-Ko-Rado Theorem with one family. And in section 2, I will explain the Erdős-Ko-Rado Theorem with two families and new result. And for the proof, in section 3, I will explain the weight version of Erdős-Ko-Rado Theorem and randomness or probabilistic method. And in section 4, I will give you several tools or ideas of proof. Okay, so first section, let me explain about the classical Erdős-Ko-Rado Theorem. Before going into the more reasonable question, I prepared this really simple question. Let bracket n be the set of integers between 1 and n. And we can define intersecting family as follows. A family F is called intersecting if for every f and f prime in F, F intersection f prime is not empty. Then we can ask the following question. What is the maximum size of an intersecting family consisting of three subsets in bracket 10? So first you may ask why we need to know this kind of question. But this is a kind of very basic question. So more generally, this is to know, we want to know a kind of maximum or minimum size of some sets or families which satisfies some given condition. So actually this kind of question is interested in for normal people who even don't study mathematics. So I prepared one example. So maybe I found this question from a newspaper. So there is some article about this question. What is the video that was mostly viewed in YouTube in 2012? And what is the number of views of the video? I guess all Koreans know the answer of this question. So let me ask this question to anybody except for Koreans. So is there somebody who knows the answer of this question? Maybe Schweizer?
I think it's this Gangnam Style.
Oh, yes. Yes. Yes, the answer is, yeah.
It's true, yeah?
Oh, yes. Oh.
Yeah, there was an idea that if it gets, it didn't get 1 billion views. This is why the end of the world didn't happen.
Right, right.
They expected the end of the world.
Right. So, yeah. It seems like Schweizer lived in Korea. So
I've never seen it.
Oh, right. Okay. So the answer is Gangnam Style by some Korean funny musicians, Psy. So if you didn't see this video, I strongly recommend that you see this video. This Gangnam is a kind of rich area in Seoul, like Beverly Hills or Beverly Hills in the United States. So, and this is some story about some guy who lives in Gangnam. And also this is important, the number of views. This number of views in 2012 is like 988 million times. This is really so many, because this is a kind of about 20% of the all population in the world. So, right. So, okay, so this is so interesting question in nature. And, but moreover, if we can answer about this, if we know the answer of this question, we can know some further knowledge. What is that? First, we can understand that there is no video which was viewed in 2012 in YouTube more than this number, right? And secondly, we know the following. If a video is in YouTube, then the number of views for the video should be less than this number, right? So this gives many informations. So, right, so for this simple question, we have same kind of interest, or we can apply the answer of this question, right? So, because, yeah, similarly. So, maybe we want to solve this problem maybe with a pen or pencil, because a pen and paper, because the number is like 3 and 10 integers, so it seems to be easy, right? But actually that's not true. So because the number of 3 subsets in bracket 10 is like 10 choose 3, which is 120, and the number of all families of 3 subsets is 2 to the 120. So this is really hard problem to do with the pen and paper without any knowledge. But of course we can use computer, right? And this number is not so much if we use computer. So we can try that. But maybe before trying computer, we want to know some kind of easy example which satisfies the condition in this simple question. So what will be really easy example? I guess the following. So let the family F0 be the family of subset F of size 3, such that 1 is in F. Actually, this is an intersecting family because 1 plays a role as the common element, right? So this is a trivial way. And if we compute the number of the size of F0, that will be 9 choose 2, because all elements in F0 should have 3 elements, and 1 is in here, right? So we only need to determine the remaining 2 elements out of the remaining 9 integers, so that the number will be 9 choose 2, which is 36, right? So, and if you use computer, you can get that this number is the answer of this simple question. So, and moreover, the families who have the maximum size is like this F0, or a family which can be obtained from F0 by some permutation, like fixing 2 or 3 or and so on, right? So, right, this is nice, but actually, right, some kind of mathematical proof may not be so easy, right? Okay. Actually, this kind of question is a kind of very important typical question in extremal set theory. And this is about, as I said, what is the maximum or minimum number of sets or families satisfying a given condition. So there are the most famous theorems in this area. First thing is Sperner's theorem in 1928, which is about the condition that for all f and f prime in the family F, F should not be contained in f prime. And the second thing is about the previous simple question that is called Erdős-Ko-Rado Theorem in 1961. And this is for the condition that for all f and f prime in the family F, F intersection f prime should not be an empty set. Okay, so, right, so this simple question is simple because we fixed the number like 3 or 10, but if we generalize the numbers, then we can have some reasonable question. So what can you change? So first we can change these three subsets into K subsets, and we can change bracket 10 as bracket n. And one more thing is about the intersecting condition. So we can define T intersecting family such that for all two members f and f prime, the size of the intersection between f and f prime should be at least T, right? So intersecting family will be one intersecting family, right? So let me define that kind of thing formally. So as we know, bracket n is the set of integers between 1 and n, and 2 to the bracket n is the power set of bracket n, and bracket n choose k is the family of all k subsets of bracket n. And a family A is called K uniform if A is contained in bracket n choose k. In other words, a family is K uniform if all members in K have size k. And then as I said, we can define T intersecting family as a family which is satisfying for all f and f prime in F. Size of f intersection f prime is at least T. Right. Then we can ask the following reasonable question. So what is the maximum size of K uniform T intersecting family in bracket n? And secondly, what are such families which have the maximum size? So such a family is called an extremal configuration. So this will be, so in the previous example here, so 988 million times will be the answer of 1, and Gangnam Style by Psy will be an extremal configuration. Right. Okay, so when we first I'd like to remark that this is a hard problem because the number of families is like 2 to the n choose k, which is 2 to the n to the k. So this is exponentially many, right? So we need to have some knowledge or method to do that, right? And okay, so but we saw a simple example, right? Simple question. So you may think that you may guess what is the answer of this question, whether you can't prove that. Maybe this looks like the answer of this question. So we can define f0t as of the family of f of size k such that the integers from 1 to t is in f. And this is a K uniform T intersecting family in bracket n, trivially, right? Because this is a common intersection, bracket n is. And if we count this like this, then we can easily show that size of this f0t is n minus t choose k minus t, right? So we may guess that this is the answer, but life is not so easy. So first, let me give several remarks. So first, this thing may not be the answer of the above question. So that's bad, but the good thing is the following. However, n minus t choose k minus t is the answer if n is sufficiently large, right? So the famous Erdős-Ko-Rado Theorem is about that. There exists an integer n0kt such that if n is at least n0kt and f is a K uniform T intersecting family in bracket n, then size of f is bounded by this number. So this number is from this example, and we can show that this kind of f0t or some permutation, so a family obtained from f0 by some permutation is the extremal configurations, all extremal configurations, right? Okay, so this is good, but we may want to ask something more. What will be? So the good thing of Erdős-Ko-Rado theorem is that this upper bound is sharp, or best possible, right? Because we have some example. But some bad thing is about this N0kt. So this does not tell about what is N0kt. So we want to know what is the smallest possible N0kt. So for the question, we can think about some observation. If n is less than this number, t plus 1 times k minus t plus 1, let me call it as a red number. If n is less than a red number, then n minus t choose k minus t is no longer the maximum size. So that's because we can define a kind of similar but a bit different family, f1t, which is the family of f of size k, such that the size of f intersection bracket t plus 2 is at least t plus 1. Then we can show that f1t is a k uniform t intersecting family in bracket n. Why is it possible? Now we consider from 1 to t plus 2, and if we get for each member in this set there are t plus 1 elements, right? So for one element, if we only consider this part, then except for one element there are t plus 1 elements, right? And for other member of f1t, maybe the other thing happens. So except for the other element, some other element, there are t plus 1 element. And if we consider the common part, that is at least t, so that's because f1t is also a k uniform t intersecting family different from f0t. Right? And if n is less than this red number, then the size of f1t is greater than size of f0t, which is this yellow number. So about the Erdős-Ko-Rado type question, this size of f1t gives the maximum size rather than this yellow number. So right, so we got this observation. So we can get the following corollary. So the smallest N0t in Erdős-Ko-Rado theorem is at least this red number, right? Because n is smaller than red number, then Erdős-Ko-Rado theorem is wrong, right? Okay, so we can make the following conjecture. If n is greater than or equal to this red number, then the statement in the Erdős-Ko-Rado theorem is true, right? But this was much harder problem because we also need to optimize the range of n. So it was solved like 70s and 80s. So in 1978, Frankel showed this conjecture only for t is at least 15 by using combinatorial tools. And in 1984, Wilson settled this conjecture for all t. Right. Okay, then you may want to ask about what happens if n is less than this red number, and that was also studied. So in 1990s, the question about when n is small was completely solved. Right, okay, so let's move to section 2, which is about the Erdős-Ko-Rado theorem with two families and some new result. So, right, until now we consider one family, but from now on we will consider two families. Then what will be a question about it? Maybe this thing will be a good question. So two families A, B are cross T intersecting so I added cross, right? If all A in the family A and B in the family B, size of A intersection B is at least T. right? So we have a family A and family B, and for each member here and each member here, the intersection between two members should be at least t, right? But one thing is, we don't think about there is no condition about two members in A or two members in B, right? And then we can ask the following question. Let A and B be K-uniform cross T intersecting families in bracket n. What is the maximum number of size A times size B? So since now we have two families, we will consider size A times size of B. And we want to also know extremal configurations. Okay, so let me say some note or remark. So first, the classical Erdős-Ko-Rado theorem with one family is for the case when A is B. And unfortunately, the method used for the classical Erdős-Ko-Rado theorem give only partial result for cross T intersecting families. So in order to solve this question completely, we need to have some new ideas or new method. Right, first, this was about cross T intersecting. The result was given for T is 1. So in 1986, Peeber showed that if n is at least 2k and A and B are K-uniform cross 1 intersecting families, then the size of A times size of B is like this, bounded by this. So this range of n is optimized here, and this value is sharp. This upper bound is sharp. And in 1989, Matsumoto and Tokushige generalized the size of members of A and B. Like A is in bracket n choose A and B is in bracket n choose B. Then we can expect this kind of thing, and so this was succeeded. And as a remark, in 2010, Gromov found an application of these inequalities to geometry. Right. Actually, this kind of result is about basic set theory. So this can be applied to any mathematics area. Okay, so we want to know about general T. So from Erdős-Ko-Rado theorem or previous result, we can easily make the following conjecture. So let n is greater than or equal to the red number, and A and B are K-uniform cross T intersecting families in bracket n. Then size of A times size of B is bounded by this number. So important thing is squared, because previously we have in Erdős-Ko-Rado theorem with one family, we have upper bound n minus t choose k minus t. But now we consider two families, family A times family B. So this should be squared. Right. So previous result is the following. In 2010, Tokushige showed this conjecture for n is greater than 2 times tk. So this is good because he got sharp upper bound about size of A times size of B, but something we need to do more is about the range of n. This range is greater than 2 times t times k, right? But this range is asymptotically t times k. So asymptotically means that if t is a large integer, then t plus 1 is similar to t. And if k is more larger than t, then k minus t plus 1 is like k. So asymptotically, this value is like t times k. But Tokushige shows that Tokushige's result is for n is 2 times t times k. So this has extra two constant vector 2. And in 2011, Tokushiga improved this range, so he got 1.443 as a constant, so multiplicative constant vector, right? But of course, we hope to reduce this by 1 to have some a kind of sharp range of n. So problem will be the following: widen the range of n as n is greater than or equal to the red number. But if this problem is so hard, then we first want to find the lower bound of n as in an asymptotic sense, like we want to have this as some kind of t times k, right? Okay, so conjecture is this. So I explained this. So recently we succeeded to show this conjecture with the asymptotically sharp range of n. So our statement is same, but the range is n is greater than t plus 1 plus delta times k. K could be arbitrarily small constant, like 0.001 or 0.000001, something like that. So actually t plus 1 plus delta is asymptotically same as t plus 1, and this k is asymptotically same as k minus t plus 1 if k is sufficiently larger than t. So we got a matched, asymptotically matched upper range of n. But there is some restriction here. So we got some range of t. So t should be at least 14, and k should be sufficiently large, right? Okay, so right. Also, we considered what is the extremal configurations. Okay, so this is our the main theorem in this talk. And in order to show or attack this statement, we consider the weight version of the Erdős-Ko-Rado theorem, and we would like to use some randomness or probability. Okay, so first let me define a p-weight version. Let p be a fixed real number between 0 and 1. So actually, for many number theorists think p as a prime number, but at this talk, p is not a prime number. P is a real number, and you need to think p as a probability, right? And let f is a subset of bracket n. And the p-weight of f is defined by mu of f is p to the size of f times 1 minus p to the n minus size of f. So it looks weird, but it is very natural if we consider some random subset. So let me define random subset as follows. F of p be a random subset obtained by choosing each element I in bracket n independently with the probability p. So more precisely, so from 1 to n, we will choose this. So we want to get some subset fp, and we will choose this element 1 with the probability p, and we will not choose this element with the probability 1 minus p, right? So this will be maybe can be chosen, and for the next element we will do the same procedure. So if we don't choose this element, then move to the next one, then we may choose this, then we will have some kind of subset. Actually, this is not a determined subset, right? This should be some probabilistic distribution, right? Each subset has some probability to be chosen, right? Okay, actually the probability is like this. So suppose that this suppose that F is a fixed subset of bracket n, then the probability that Fp, the random subset is F, is just like this. That's because suppose that F contains size of F is there is some, we fix on F and there is some size of F. Then let's say this is the element of F. Then what is the probability that our random subset is this set? That will be, so for those elements, we need to choose those elements, right? And for each element, the probability is P. So that will be P to the size of F. And for the remaining element, which was not chosen in F, the number of elements will be n minus size of F, and the probability will be 1 minus P. So that will be 1 minus, the probability will be 1 minus P to the n minus size of F. Okay, so this is defined in that way. And we consider the P weight of a family F as mu of F is sum of mu of F, summing over F is in the family F. So this is a kind of natural definition. Then, right. Then with this new weight, we can define, we can ask P-weight version question. So let A and B be cross-T intersecting in bracket n. And what is the largest number of mu of A times mu of B, right? So until section 2, we asked this kind of question, which is about the largest number of size of A times size of B. But now, from now on, we will consider the weight. So actually, it looks like two questions are totally different, because in here, each subset has same weight 1. So we count 1, 2, 3, something like this, right? But in here, the weight is different for each element, each member, right? So that depends on the size of F. So some element has more higher weight, and some element has lower weight. So two questions are looks like totally different, but actually that is not true. So it is strongly related to. So two things are strongly related. So more precisely, this question with our P weight is related to an NP uniform version. So why NP is here? That's because that's from the definition. So we consider the random subset when we define mu of F. And what will be the expected size of this random subset? So now we have n element, and we choose each element with the probability P. So the expected size we have will be n times P, right? So the expected size of this random set is n times P, and moreover, if n is sufficiently large, we can understand that the size of Fp is really concentrated around the expectation with very high probability. So we can simply assume, so briefly speaking, we can think that this random set as a subset of size np, or around np. So we can consider this as np uniform version. So there is some relationship. Actually, that's why we can use this P-weight version to show this uniform version. Okay, so second remark is the following. So since this mu was defined by a random subset, so we can use some randomness or a probabilistic method. So we have some machine so to do, right? Actually, so this P-weight version is a kind of concept which was studied already in literature. So since this P-wave version is natural, many mathematicians studied about this. So in 1998, R. Swed and Kachan-Turian got the complete answer, like classical Erdős-Ko-Rado Theorem with this P-wave version. But I don't want to explain that precisely. Okay, so with this P-wave version, so if we consider the previous question about the Erdős-Ko-Rado theorem, we can make the following conjecture easily. So for every t and n and p, we range this. So p is between 0 and 1 over t plus 1. Then we have the following. If a and b are cross t intersecting, then mu of a times mu of b is bounded by p to the 2t. So important thing is this range of p. So that is given here when we consider one family with the P-wave version. The range of this p was appear here, right? So we can, in the conjecture, we can ask the same question. And about two family version, but the previous result using Friedrich's proof only gives a smaller range of p. So the range of p is like upper bound is 0.69 over t plus 1. So this is much smaller than 1 over t plus 1. So to solve this conjecture, we hope to enlarge the range of p. And recently we succeeded in that. So we solved the conjecture with the range of p in the conjecture. So this upper bound is 1 over t plus 1. So actually this is a kind of important issue. Like in Erdős-Ko-Rado theorem, after the statement of Erdős-Ko-Rado theorem was appeared, so the improving the range of n was the main topic, and that was it took 20 years to solve the problem. So in here also the range of p is really important, but we fortunately got the matched range of p. But the bad thing is that we have some condition about t. We only showed this when t is at least 14. So maybe for smaller t, maybe some new idea or technique is needed, right? Okay, and from here to our main theorem about k-uniform version, we apply the cross-Katonas theorem, but I don't want to discuss about it at this time. Okay, and let's move to several tools. Right. First tool is about this. So we will consider, until now we consider subset in bracket n. We will correspond each subset to walks like this. So let me give you one example rather than a precise definition, because that will be easy to understand. So let f is 1, 3, 6, 7, 11, 12 in bracket 14. Then we want to draw a walk here on grid in the plane. So this walk starts from the origin. And since 1 is here, the first step goes up. And since 2 is not here, the second step goes to the right. And 3 is here, so third step goes up. And since 4 and 5 is not here, fourth and fifth step goes to the right. So, and so on. So we can define this kind of natural walk and that natural correspondence between subset and walk. Actually, this kind of walk is a kind of one of topic in combinatorics. So now, especially at KAIST, Professor Dong-Soo Kim and Jang-Soo Kim works on grids in the plane, right? Okay. So what will be a good thing when we think this kind of walk? Maybe I think the following is that. So we can ask the following question. If f is in A, then is there some restriction to B? So this is what we want to have, because now we want to bound mu of A times mu of B, right? So we want to know that if A is large, then size of B is small, right? By some restriction. So this is a natural question. And actually this walk gives us some nice answer about it. So let this is some f. Then, there should be some line here. So there is a line like this. So that is about y is x plus t. And now we consider t intersecting family. So I draw this line. And we consider y is x plus t minus 1. So you can imagine the line. And we can get this kind of a walk obtained from f by a reflection with respect to the line y is x plus t minus 1. So by this line, these two things are, this is obtained from here by a reflection, right? Of course, there is some, this part is impossible, so I draw like this. Okay, and we say that this is dual of f. Then we can show that the size of f intersection dual of f is at most t minus 1. And that's because if this goes up, this goes to the right? So there is no intersection at this part. So only intersection happens here. So that gives us this kind of answer. And as a corollary, we can say the following. Let A and B be cross-T intersecting. And if f is in A, then the dual of f is not in B, because this intersection is less than or equal to t minus 1, right? So this will be a useful fact, right? Second tool is about randomness. So using randomness, we can show the following lemma. Suppose that all walks in f hit the line y is x plus lambda. Then mu of f is bounded by p over 1 minus p to the lambda. So the proof is the following, briefly. So let WP be an infinite random set whose ith step goes up with the probability p and to the right otherwise independently. So WP is also a kind of probabilistic distribution, right? When someone draw an infinite random walk, then there is some probability. Of course, there are infinitely many infinite random walks, so probability of one random walk will be 0, measure 0, right? But if we consider some family, then that has some probability. Okay, then we can show the following. So mu of f is bounded by probability that this infinite random walk hits y is x plus lambda. So the two things are related. Two things are based on the same property, because mu of f, all walks in f hit the line y is x plus lambda, and this infinite random walk satisfies the same condition. But this is inequality, because in here we consider some finite random walk. So that stops at nth step, but over here we consider infinite random walk. So this is gives an upper bound, and also we can compute this with some recurrence identity. We can compute this like this: p over 1 minus p to the lambda. Okay, so this is good because we got some upper bound, nice upper bound about mu of f like this. So in order to use this lemma, we can define the following. Lambda a is the largest integer lambda such that all members in A hit the line y is x plus lambda. Then so we maximize this lambda, then we have a better upper bound. Okay, then let me briefly say, this is the last slide. Let me briefly say about the basic ideas for our p-wave version of Erdős-Ko-Rado theorem. Right, so we want to show that this is true. So if A and B are cross-T intersecting, then mu of A times mu of B is bounded by p to the 2t. And our range is like this. P is less than or equal to 1 minus t plus 1. So we start with the following. Let A and B be left-shifted maximal cross-T intersecting families in bracket n. So you know what is maximum. So we want to put members as much as possible. But the definition of left-shifted is about the following. So here, so this is about a subset. So for a family, we have many walks like this. So then we would like to shift that to the left as much as possible. So then we have a kind of compact family of walk in the left side, right? So because of some technical reason, we need to do that. But I don't want to say about it. Actually, that is one of the key idea of this theorem, this proof. So, but just you can assume that this is moved to the left. And okay, then we consider lambda A plus lambda B. This is important number. So first we can show that lambda A plus lambda B is at least 2t. The reason is from this. So if this lambda A plus lambda B is less than 2t, then we can have some walk in F in A, and we can also have some walk like this in B. So, and we know that these two walks, the size of intersection between these two walks is less than or equal to t plus t minus 1. So that gives us some contradiction. So this value should be at least 2t. And secondly, we can show the following. If lambda A plus lambda B is at least 2t plus 1, then mu of A times mu of B is bounded by p to the 2t, or a bit more, with a 1 minus epsilon factor. The reason is from this lemma. So we got some nice upper bound of mu of F. So if lambda A times lambda B is, okay, so from this lemma, we have upper bound of mu of A times mu of B as so I applied this lemma for A and B. So we have this kind of inequality. Then this will be this. And our condition is that lambda A plus lambda B is at least 2t plus 1. So this is bounded by this, and with our range of p and this range of t, this is smaller than p to the 2t. So we can get this one. So actually, the condition t is at least 14 is appears when we make this kind of inequality for the last thing from here to p to the 2t. Okay, so the remaining case is when lambda A plus lambda B is 2t. Actually, this part is the highlight of the proof, but based of the time limit, I want to skip this proof. But for the remaining case, we need to have a kind of more precise computation or some new idea. Okay, thank you for your attention.